Okay, so I think we're just about ready to get started. Welcome to the 2024-2025 series of online seminars by the Working Group on Active B Stars of the International Astronomical Union. So it's good to see everyone back after a longer summer break. And today we're lucky to have with us Hema Anilkumar. Hema is a PhD candidate at Christ deemed to be University in Bengaluru, India, where she's working under the supervision of Dr. Srija Karta and Dr. Blesson Matthew. And today, Hema is going to be telling us all about X-rays from Herbig Ae B stars. So without further ado, Hema, please take it away.
Thank you, Alex. I'm Hema. I'm a PhD candidate from Christ deemed to be University. My PhD supervisors are Dr. Srija Karta and Dr. Blesson Matthew. I mainly work on X-ray emission from pre-main sequence stars, but today's talk will be on a recently published paper, that is, do Herbig Ae B stars emit X-rays? So this is a snapshot of our paper, which was published recently, and I'm extremely thankful to my supervisors for their support and also the co-authors for their valuable guidance. Okay, so moving on. This would be the outline of today's talk. So first, I'll be talking about X-ray emission in stars. So X-ray emission in stars. Now here we see a color magnitude diagram. We see that the stars of almost all masses and phases emit X-rays, but the X-ray emission mechanism differ depending upon the mass and phase of these stars. So to understand this, sorry, I think something. Yeah, sorry. Yeah. Okay, so to understand this, let's look at the structure of stars. So here we see a pictorial representation of stars of mass similar to Sun, low mass star, a massive star. So in the center we see we have the Sun, which is a G2V type star. These type of stars have a radiative interior and a convective envelope. And we know that all the stars rotate around their axis, but this rotation is different at different latitudes. And this is called as differential rotation. So when so the interaction between the convective layer and the differential rotation generates what's called as the alpha omega dynamo, and this dynamo is responsible for the generation of X-ray emission in the Sun. Now moving on to the low mass stars. These stars are more convective in nature. And they have lower core temperatures, which leads to slower burning of which leads to slower burning. So as a result, we find a lot of heavier elements present in the photosphere of these stars, making convection the main source of energy transport. In these stars, we also expect certain type of dynamo to be at work for the production of X-rays, which is still an active field of research. So this is an X-ray image of the Sun, which is taken from the soft X-ray telescope on board the Yokot satellite. We also see the stellar flares and the 11-year cycle of the Sun. So these solar features offer insights into X-ray emission mechanism that can also be applied to other stars. So now moving on to the massive stars, X-ray emission in massive stars. X-ray emission in massive stars. In these stars, there is no convective layer. Because of this, they are extremely high in temperature, which exceeds 20,000 Kelvin. These stars begin burning hydrogen much earlier than the other two cases. So due to this, they develop a radiative outer layer where no dynamos can be formed. So these stars possesses massive and fast winds driven by radiation pressure and radiation-driven instabilities, which leads to the formation of shocks on the surface of the star. This type of X-ray emission occurs in O and B type stars. So this is a summary of how X-rays are generated in low mass stars and massive stars. So in low mass stars, we see magnetic dynamo activity, coronal heating, stellar flares, and magnetic reconnections happening. In massive stars, it is because of the radiatively driven winds and wind shocks, and also because of the magnetically confined winds. So now we saw about the X-ray, how X-rays are produced in low mass stars and massive stars. But the late B-type and early A-type stars, they do not have enough temperatures, hot enough temperatures for the wind shocks to collide and generate X-ray emissions. And neither do they have convective layer like sun or low mass stars for the magnetic dynamo to be at work. So theoretically, these stars are not supposed to emit X-rays, but observations say otherwise. So now, what are Herbig Ae stars? So Herbig Ae stars come under this category of stars which I just discussed. So these stars were first identified by Herbig in 1960, and later Water and Watkins defined these stars as stars having spectral type A or B with emission lines. And these stars would have infrared excess from the circumstellar disk, and the luminosity class varies from 3 to 5. Also, these stars are of they have masses from 1.5 to 12 solar masses, and the spectral type varies from B0 to F5, age 0.1 to 10 million years. So as we discussed, as we just saw that these stars show infrared excess due to the presence of disk. They also have H-alpha emission due to the accretion happening from the circumstellar disk onto the star. So this is so here is an image of HAeBe Auriga taken from the near infrared telescope HAeBe. Here this is the best example of showing that Herbig Ae stars have the presence of disk, and in the right there is a spectral energy distribution of the star, of the same star, which is showing an excess in the infrared because of the presence of the circumstellar disk. So now, can these type of stars emit X-rays? So theoretically, these stars are radiative in nature, and they are supposed to be X-ray dark. But this is an image from our work where we see stars from B1, B0 to F5 are emitting X-rays. So earlier, many studies were many studies were performed, and they suggested late type companions and star magnetic interaction as the possible X-ray emission mechanism in these stars. So in our study, we examined these mechanisms, and we aim to constrain the dominant sources of X-ray emission through correlation studies. So data and methodology. Now, first we obtained the optical sample from the Viok et al. 2018. Then we cross-matched this with the Chandra data archive, where we obtained 62. We obtained the X-ray observations for 62 Herbig Ae stars. Upon checking these 62 observations, we saw that 44 Herbig Ae stars were detected in X-rays. And since we are trying to study the for the comparative study, we consider the T Tauri star sample from the COUP data, and we use the CIEO tools for data reduction, and the spectral analysis and light curve analysis was performed using HEASoft software. So we obtained X-ray parameters such as plasma KT and LX of the Herbig Ae stars from the spectral fitting using 1T or 2T APEC models. And then we compare the X-ray properties of Herbig Ae stars with that of T Tauri stars. So here is an image of LX versus L-volt for Herbig Ae stars and T Tauri stars. So here we see that both Herbig Ae stars and T Tauri stars emit X-rays in almost the same luminosity range. But when we normalize this with the bolometric luminosity, we clearly see that the T Tauri stars are saturated around minus 3.6, but for Herbig Ae stars, we see a decrease in the X-ray luminosity with increasing temperature. So now to see if accretion or to see if disk or accretion is influencing the X-ray emission, we perform correlation studies. So what we did was we obtained the spectral index from in the band 2 to 4.6 micron, and we correlated this with the LX by L bole fractional X-ray luminosity of Herbig Ae stars. So what we see here is the majority of Herbig stars, they belong to class 2 and flat categories based on the classification scheme by Green et al. 1994, and we observe no correlation here. So the LX by L bole is consistent with in both Herbig Ae stars and T Tauri stars, and this suggests that X-ray emission is independent of the presence of the disk. Next is we study if X-ray emission is driven by the accretion processes. So we know that Herbig Ae stars are actively accreting material from the circumstellar disk through magnetic field lines. So from this, when the material from the star, when the material from the disk transfers onto the star, accretion shocks are created on the surface of the star. So based on this, we have to see if this is the origin of X-ray emission, we have to see a correlation between the fractional X-ray luminosity and the H alpha luminosity. But here, as we see, we do not observe any. We do not observe any correlation between these two. Sorry, we did not observe any correlation between both the samples, that is T Tauri stars and Herbig Ae stars. We also performed Pearson's test to check this, and we did not observe any correlation. So this suggests that X-ray emission is independent of the presence of disk or accretion and is likely to be driven by the intrinsic stellar processes. So now in the literature, many theories were proposed to explain the X-ray emission mechanism in these stars. So one of them was magnetic accretion from the disk to the star. So now by the correlation studies, we have ruled out this model. So the next we would be seeing if an undetected low mass companion is contributing to the X-ray emission. So we did a thorough check of the literature and studied individual stars if they have any binary or companions present in them, and we identified 19 stars in our sample to have binaries or multiple companions, and 25 stars we identified them as. 25 stars were identified as single stars. So these were confirmed as single, or there were no any evidence of the presence of companions. So now we'll discuss about the various types of companions that we observed in our sample. So the first is the planetary companions. So sorry, before that, what we observed from a study was when we obtained the X-ray parameters from the spectral fitting, we saw that the plasma temperature for single Herbig Ae stars were below 2 keV, and were below 2 keV, and for the Herbig Ae stars with confirmed companions, we observed that a higher plasma temperature was observed in them. So studying the companions, so we discuss about this 25 single Herbig Ae stars. So some of the Herbig Ae stars were confirmed using high resolution studies and high contrast imaging studies. So we found 7 of them being studied using this method, and and 7 of these stars had planetary companions rather than stellar companions, and all of these stars, all of these 7 stars have plasma temperatures less than 2 keV. Also, this is an image of HAeBe Aurigae by studied by Boccaletti et al. 2020. So the spirals which we are observing here, they suggest that these spirals are because of the presence of 2 planetary companions. So now the other type of companions that we found in our sample was Herbig Ae systems. Like both the stars are of similar mass. So now we observe 4 stars of such type. One is AKSCO, BD plus 651638, PDS 69, and V892 tau. In these stars, no other low mass companions were reported. the SEO was studied using high resolution data, and it was confirmed that no other lower mass companions were present in this system. This star consists of F5 type stars. Both the stars are of same spectral type and almost similar masses, while other three stars, these are very less steady. Only that both the stars are of B type. V892 tau is a triple star system where the central source is a binary of a spectral type of later B spectral type, and it is associated with an M-type companion. So in these stars as well, we observe the plasma temperature to be less than 2 keV. So the next type of system that we saw was Herbig Ae stars with low mass system. So we found 6 such stars in our sample. And these stars had multi-epoch data, so we performed light curve analysis of these, and we saw that all of these stars had which had low mass companions, they showed flaring or variability in their X-ray light curves. And the shape of this X-ray light curve was very similar to how it is for how we see in low mass stars, which is rapid enhancement in the contrast and followed by a slow decay. So such flaring or variability was not observed in single Herbig Ae stars. And the X-ray temperatures of these stars were also consistent with what we observed in the KT versus LX plot. It was greater than 2 keV. So now from the studies of the companion and from the companion studies and the LH alpha versus from the correlation studies, we rule out that magnetic accretion. We rule out magnetospheric accretion model and the contribution of low mass companion as solely being the reason for the X-ray emission in Herbig Ae stars. So further now we see if further okay. So further we see that other emission mechanisms that were proposed for these type of stars are colliding winds, which is similar to OB type stars, or magnetically confined wind shock model. So, but these two models require the presence of require the presence of magnetic fields. So, sorry, there's a glitch here. I'm unable to change the slide.
Maybe stop sharing and redo it, or get out of this tool and relaunch it.
Sorry for that. So we checked if there are any magnetic field studies for Herbig Ae stars, and we saw that very few Herbig Ae stars were found. In very few Herbig Ae stars, magnetic field were detected, and from the studies by Alician et al. 2009, Herbig et al. 2011, and Havinen et al. 2015, the magnetic field in these stars were found to be ranging from 10 to few kilogauss. Also, Havinen et al. 2019b found in their study that Herbig Ae star possesses much weaker magnetic fields, around 500 Gauss, compared to that of their lower mass counterparts, which have magnetic fields in kilogausses. So now, when we cross-match this data with our sample, we saw that 15 stars in our sample had magnetic field measurements available. And among these 15 stars, 11 stars did not possess any companions in them. So we see that there is a possibility of magnetic fields to be present in Herbig Ae stars, and this could be the reason for the X-ray emission in them. But how these magnetic fields are present, that is still unknown. So since we saw that the Herbig Ae stars could possess magnetic fields, so this raises a question if the origin of X-rays in these stars are coronal in nature. Telesky et al. 2007b and Gunther et al. 2009 and 2000 studied high resolution spectrum of Herbig Ae stars HAeBe Aurigay and HT 163296 using XMM Newton and Chandra telescopes. They obtained, in their spectral analysis, they obtained the plasma temperature of these stars to be less than 2 keV in both of their studies. And they also studied the helium-like triplets of O7, where they found that a high forbidden to intercombination line ratio at 22.1 angstrom and 21.8 angstrom respectively. A high F by I ratio points to lower density regions for the X-ray emission, such as the corona. So both these studies from the results obtained from their studies, both these studies reject the accretion shock model and companion hypothesis. Now, Telesky et al. 2007b and Gunther and Schmidt 2009 suggested that wind shock model or magnetically confined winds could be responsible for the emission of X-rays in Herbig Ae stars. So we saw that X-ray emission in Herbig Ae stars could be due to the presence of magnetic fields, though the origin of magnetic field remains unknown. So from other studies like Herbig et al. 2009, they found in their study that the magnetic field strength increased with the X-ray luminosity in young Herbig Ae stars. This suggested that X-ray emission diminishes as they approach the main sequence. So this agrees very well with the model proposed by Tout and Pringle, where a non-solar dynamo operates in rapidly rotating A-type stars based on rotational shear energy. And other possible mechanisms for X-ray mechanisms could be from the magnetic activity, could be due to fossil fields or magnetically confined wind shock models. So the conclusion from the study was from out of 62 Herbig Ae stars that we obtained from the Chandra data, 44 stars were observed in X-rays. These stars have this study has a detection rate of 70.9%. The Lx for these stars range from 10 power 28 to 10 power 33 ergs per second, and the fractional X-ray luminosity was between minus 3.5 to minus 10, which is in the region in the mid region between what is observed for T Tauri stars and massive stars. So 50s from the binaries from the companion study that we did, we saw that 56.2% of the sample are single Herbig Ae stars, and these and also from the plasma temperature studies, we saw that 50% of the single Herbig Ae stars, which were fit with one temperature model, had plasma temperature greater than 2 keV, and 80% of these are not sorry, again there's a glitch. I'm really sorry about this. So So from the X-ray temperatures, from the plasma temperature studies, we saw that a majority of single Herbig Ae stars, that is about 50%, the plasma temperature for these stars were less than 2 keV, and less than 2 keV, and for the stars with confirmed companions, we saw a plasma temperature to be greater than 2 keV. So from these correlation studies and the companion study, we have ruled out the magnetospheric accretion and the presence of low mass companions to be the origin for X-ray emission in Herbig Ae stars. So from this study, we see that the magnetic field detection and the coronal region as a source of X-ray emission. This favors the shear dynamo theory and also the fossil field hypothesis or magnetically confined wind shock models. In the future work, we plan on studying these peculiar Herbig Ae stars systems that we discussed about using Chandra, using high resolution X-ray spectroscopy from Chandra or XMM Newton. And we also plan on combining the X-ray data with that of optical or UV to correlate the X-ray to correlate the X-ray studies and the results obtained from the to correlate the optical properties and the X-ray emission properties. Yeah, so that's it. Thank you.
Okay, let's everyone thank Hema for a very nice presentation. I see some hand clapping emojis in the chat. So thank you very much, Hema. We have quite a bit of time for questions. So if yeah, I see that Yael already has a hand up. So please go ahead, Yael.
Yeah, I do have quite a lot of questions. Thanks for this nice seminar. Okay, I start with one and then I let others ask questions, and if there is nobody, I ask the others. Could you go back a little bit in a few slides back?
Yeah.
No, it was, I think it was probably later than that. Yeah, the next one. Stop. This one. No, this one. Okay. So you mean here the mechanism for the X-ray emission could be fossil fields or magnetically confined winds. I'm not sure I understand the "or" in this sentence, and I'm not sure exactly what you would have here. So you're suggesting it would be a coronal emission, a little bit like the other young PMS, so magnetic reconnections, or fossil field or magnetically confined wind. But how do you see this difference between fossil field and confined winds?
Okay, so based on the study by Herbig et al. 2009, so they suggested that as the pre-mean sequence star reaches to the main sequence phase, they observed a diminution in the X-ray emission. So, so based on that study, we could say that the fossil field so when the pre-mean sequence star reaches to its mean sequence, so they from their study, it is seen that the magnetic field and also diminishes as it reaches the mean sequence. So during this, they also observed a diminution X-ray emission. So in that correlation, we have to not see. So when we compare a sample of data, we are not based on this. Most of the pre-mean sequence stars have to show a higher X-ray emission compared to the main sequence stars. So now from whatever studies that we have done, we only we can only say that magnetic field could be present in these stars, and they could be the reason for the X-ray emission in them. Other than that, we really don't know how the magnetic field could be present in these stars.
Okay, my question basically is, why did you put or in the last sentence here?
Because these studies were performed on, I mean, these studies were performed quite I mean, the sample of these stars were like very less. So we still don't know if we are really observing this pattern in these stars, or if the magnetic field is not um, so
So maybe I can jump in here a little bit, if you don't
yeah,
mind.
sure.
I think what Yael is getting to here is that the fossil fields and magnetically confined wind shocks are basically the same scenario. So I don't know if you put or here just to say that there are kind of two ways of designating this, or maybe
Okay.
that's what we were getting to here. Does that sound reasonable, Hema?
Yeah, I mean, until now, we just know that magnetic field could be responsible, but we really don't know as to which model would be, I mean, which model would actually suit this. So that is why I mentioned or there. So yeah.
So actually, maybe just to piggyback off of this, I'll use my prerogative as a as the presenter of the seminar, or not the presenter. I mean, sorry, the host or whatever. But so I think that there's something interesting here, right? Because if you're considering both coronal and fossil fields, my understanding, and it's very limited, so I apologize if this is a naive comment and question, but I know that for intermediate T Tauri stars, I think there was a study by Villebrun that showed that, basically as they go through changes in their internal structure, you kind of see maybe fields appearing, and they could be seed fields for fossil fields later on in the life. I wonder if Herbig Ae stars might undergo similar changes, which could explain why some might show characteristics that are more consistent with coronal X-ray emission, and some might have something that's closer to magnetically confined wind shocks. So I was wondering if you'd seen any correlations with kind of how close to the main sequence the star is, and if you'd inspected the X-ray light curves, because you would expect different behaviors, right? If it's more coronal in nature, then you might expect some flaring, perhaps naively, I don't know, as you see in the younger stars. And if it's magnetically confined wind shocks, then it might have to do more with rotational modulation or something along those lines. So did you observe any of these differences?
Yeah, so when I was talking about the companion studies, so we saw like around 6 of the stars in our sample had low mass companions, and so when we plotted, and these stars also had multi-epoch data. So when we plotted the light curve of these stars, we observed some variability in them, or flaring also occurred in these stars. So supporting this, even the plasma temperature for such stars was greater than 2 kV.
So I guess the question is, have you done something similar for the seemingly single stars?
Single stars, yes. So in those single stars, we did not observe any flaring. I did not put that light curve in this PPT, but yeah, so none of the light curves showed any flaring in them, except for V892 tau, that is the binary system of similar mass. So this star sort of showed a flare, like a flare, but much details are not available regarding the star. So except for that, for the majority of the single stars, we have not observed any flaring or variability in them.
Thanks. Any other questions? Yes, Yael.
Yeah, sorry, as I said, if nobody takes in, I have many questions. So when you were mentioning about binarity, how did you know that they are binaries? Is it just visual companions, or is it, I mean, radial velocity studies? What is it? So to get an idea of the period, the orbital periods, because then I can ask us a sub question.
Yeah. So these stars, I mean, I can just confirm the binarity of these stars based on the literature studies. So in the literature studies, some of them were mentioned as spectroscopic binaries based on the spectral studies that they had performed, and some were studied using high resolution data, like the SCO star. So yeah.
Do you see any difference? Because at some point on one of the slides, you are mentioning colliding winds. And of course, colliding winds, you don't have any flares, that's for sure. But also you would see modulation with the orbital period, but only in some cases, and especially if you have very far away stars, you don't really expect to have very strong colliding winds. So that would make a difference between the ones detected by radial velocity with low period, short period, and the one detected by high resolution studies, which would be very long period cases. Do you see that difference?
No, I mean, I have not gone in detail with that. So I would look into this actually. Yeah.
And if I continue about the winds, did you get any diagnostic in UV telling you if there is some wind or not? What's the strength of the wind?
We have not checked the UV data for this yet. I mean, that would be in the future studies. So.
Okay, so you don't have IUV data or stuff like that.
Yeah.
Oh, okay. Activity also, if it's a coronal activity, you would have, I've seen you have checked H alpha, but did you check the calcium triplet? Because the calcium triplet is quite obvious indicator of the coronal activity.
We have not checked the correlation between the calcium triplets and the X-ray emission. So yeah, I mean, I would look into it actually. So
yeah, because if you have H
Excuse me.
alpha, you probably have optical, right?
Pardon?
If you have H alpha, you probably have an optical spectra of some sort. So maybe it covers.
So H alpha as well, we obtain the H alpha from literature studies for these. But in the future, we would be looking into the optical spectra of all of these stars, and yeah.
Okay.
So I think I heard someone else trying to.
Yes. This is so I have joined from Srija's account. This is Blessing Matthew. I mean, so we both supervise Hema. So I thought I should respond to a couple of queries which were asked right now. So yes, we have optical spectrum for these stars, and primarily we had looked into let's say oven lines, oven forbidden lines, right? I mean, if as you know, 6-3 006363 doublet. I mean, that is basically an indicator of wind signature. So, but then maybe in general, we see these oven lines for a very subpopulation, right? No, so when you look into the sample which we are talking about for the single stars as well as for cases where companions are there, you don't see any clear. We are not seeing any clear distinction as such, and but then we need to look much carefully along that lines. And regarding the calcium triplet, yes, that could be used as an indicator, but then from our experience dealing with the spectra of classical B stars, I mean, which primarily don't have any chromosphere, you generally see calcium triplet in those cases also. So in the context of hot stars, I'm not quite sure to what extent we can use calcium triplet for that study. Again, the statistics, if I look at a population of, let's say, Herbig stars, very few percent show calcium triplet in emission. And I had done this analysis way back where I tried to correlate whether this is a function of any specific property of Herbig stars, for which I didn't get any solid answer. Right. I mean, we had compiled some information from the literature also, very specifically the studies of Haman and Person from there, I mean, all the way. Yeah, so the advantage we are having is, yes, we have optical spectra of the sources, but then UV, we should look into, we should do some observations, or we should look into that data. I'm not quite sure whether UV data is available, for example, IU and all. I mean, I think Hema had done a quick search. I mean, she didn't find any probably, but then we can look into it. And obviously, UV is going to be very key indicator here, because considering the C4 lines and all in those systems. So yes, I mean, yeah, it could be done. Yeah. Does that answer your question?
Yeah, sure. And of course,
Yeah.
if you have checked calcium triplet in some cases and that you don't find a clear correlation with the X-ray emissions, that means that it's not coronal. So that's very interesting. Right. Did you do any
Yes.
any comparison with the A studies of Jan Robrade? Because he has, so those are not young stars. Those are main sequence objects. But he does have for a few A stars flares indicating some activity, which is quite unusual, because I mean that's not normal, right, for those A star. But maybe the one you have could be precursor of what he sees, right?
Right. I mean, the trouble with calcium triplet is we are talking about, let's say, low volt line in those contexts. I mean, particularly during our study on classical B stars, I mean, these are really hot stars with a gaseous disk. We are not even talking about a bigger disk like we generally see in Herbig stars, or the role of magnetic fields. None of that comes into the picture for classical B stars. I mean, but one puzzle we still haven't sorted out is we are seeing calcium triplet primarily in emission for some of the classical B stars. I mean, for those lines to form, we really need a low temperature environment for that. And considering the temperature environment, let's say the disk temperature for a classical B, ideally, I shouldn't expect calcium triplet in there. So we are thinking hard to see like how these are formed. Probably it could be like some fluorescence or some other mechanism is happening. So where I needn't have to worry about the real volt of the real EV of the line, but it will somehow get populated to the upper level. So that is some understanding, some knowledge, some wisdom we got from classical B studies. So that's why I was saying like calcium triplet is more like an open field, at least for me, where things are not sorted yet, because much possibilities are there. Because if you look at T Tauri spectra, for example, you will get another calcium line, calcium H and K there in emission. So the natural question we were asking was, as part of some of our studies, where if calcium triplet is in emission,
why is it you are not seeing H and K in emission? In some cases you see, some cases you don't see. We have some tentative answers because if you look at the line diagram, the term diagram, you could see that they are not much far. I mean, so again, this may be giving us some indications. So, so yes, I mean, so there is a scope, as you said, for a extensive analysis by combining, let's say, the stellar parameters with respect to the spectral parameters, and then you see like how X-rays are behaving in those contexts at different epochs as a function of, let's say, age or whatever, or spectral type, let's say, for that matter. So that's something interesting. So, and primarily the sources which Hema showed, I mean, those binary sources, binary Herbig stars. I mean, we are planning some follow-up observations on those as well, right? I mean, so so what we are excited about this is like there wasn't much study of late on the X-ray emission from Herbig systems, or more like intermediate mass pre-main sequence systems. And so, but then the previous studies were mostly in a confused state, like, is it due to binaries or is it due to the original star emission? If that is the case, then why is it? Is it coronal? Then what's the role of magnetic field? All these issues were there. I mean, so it's good that we are seeing some new insights here, but much could be done in this direction from further analysis and observations. In the scope of the present work, we could only include this because there were some additional analysis which we did, which we kept aside, obviously, because it was basically diverting from the main theme, right? No, so sorry if my answer was long. So
No, that was very interesting. Thanks a lot.
yeah, thanks.
Wonderful. Any more questions for Hema? Okay, in that case, I think maybe we're ready to adjourn for today. So I do want to thank Hema once again for a wonderful talk. It's sparked quite a bit of discussion, and you know, I think the value of these seminars is that maybe it brings together people who hadn't necessarily met or worked together before. So maybe some new discussions have been open today. So I thank you all for that. And actually, this was a nice segue because BE stars were mentioned, and next month we'll be having a seminar on the presence or not of magnetic fields in these stars. And so therefore we'll be convening on November 19th. And Patrick Stanley from the University of Delaware will be regaling us about these BE stars. So thank you once again, everyone, for connecting. This seminar will be available on YouTube after, maybe a few days. And thanks again to Hema. I hope you all have a wonderful rest of your day or night, as the case may be. And we'll see you all in a month.
Bye-bye.
Thank you all.